Welcome back, everybody. We've already been introduced to exponential functions and learned some of their basic properties. How quickly they grow, if they're an exponential growth function, how quickly they shrink, if they're an exponential decay function, and how to deal with some of those terms like initial value and common ratio. In this video, I want to talk specifically about how to solve equations that involve exponential expressions in functions. There are a couple of key properties that we'll learn here, but in general we'll keep expanding on what we talked about in the last few videos. We've already looked at a lot of functions that have this form. This is the prototype of an exponential function, and as we discovered before, a represents the initial value. That is the value of this function when x equals 0. Remember, this makes sense because whenever x equals 0, b raised to the x power is 1, no matter what b is. So a times 1 will result whenever we have x equals 0. We've referred to b as the common ratio. So every time x ticks up, usually by integer values, this equation gets multiplied by b. We start with an initial value of a, and we keep multiplying by b. It's in fact because we're doing this constant multiplication that exponential functions grow so quickly. X is of course the exponent in this case, but it's also our independent variable. So this function's really asking us a question. Now this is the same question we ask in every function, but x is in a different place here. Now we have x in the exponent. So as we increase x and we multiply by b more and more times, f grows, as we say, exponentially. So, for example, g of x is an exponential function. X is our independent variable and tells us how many times we're multiplying by our common ratio 3. So to ask ourselves the question, what is g of 8? All we're doing is inputting 8 for x. Well, let's jump to the calculator and figure out what this is. So our initial value was 1/2. So when x equals 0, this particular function has a value of 1/2. But we're going to multiply that by 3 to the x, and in this case x is 8. Let's write that down. The most frequent way that you'll see this interpreted is with x as time, or the amount of time that's passed. Now this might be time in seconds, it might be time in years, it might be time in millennia. But what we're often interested in is what happens after a certain number of time periods have passed. How much has a particular population grown if we have an exponential growth function, or how much has it declined if we have an exponential decay function? Let's look at an important property of exponential equations here, and we'll see how all of this works in some examples. This property uses b as the base of an exponential expression, and x and y as the independent variables. All this is saying is that if we have a common base raised to 2 different powers, but each of those expressions is equal to the other, then it must be the case that those exponents are also equal to each other. Here is the world's simplest example. If 3 to the x equals 3 to the 5, it must be the case that x equals 5. Now this doesn't really seem like an exponential equation in the way that we've been looking at them, and it certainly doesn't have the kind of weight that a lot of the real-life examples that we will see do. But we are still solving for x in an exponential equation. Of course, the most important thing to remember here is that those bases have to be equal. It doesn't make any sense to say that if 3 to the x equals 5 to the y, that this somehow implies that x equals y, or even that we can simply solve for x or y. This just isn't the case. So a lot of the work that we have to do is going to be manipulating expressions in order to get the same base. Let me give you an example. So 4 raised to some power x is equal to 64 raised to the 3rd power. We're trying to solve for x in this case. Well, we can't directly tie the x and the 3 to each other. That doesn't make any sense here because we don't have equal bases. But here's where the trick of all of these problems comes in. In many cases, the bases will be exponentially related to each other. When I say exponentially related, I mean that one of them is likely to be a power of the other. Then this problem becomes a simple one of just using the properties of exponents we already know to solve for x. So what is the relationship between 64 and 4? Well, 64 is 4 cubed. So let's rewrite that. Now we've written the exact same expression, except we have common bases here. Our next step is just to use the rules of exponents in order to solve this equation. Since we know that raising a power to another power means we multiply those powers, our right-hand side becomes 4 to the 9th power. And now we have exactly the kind of expression that we were looking for in the highlighted portion of the property above. 4 to the x equals 4 to the 9th. So because the bases are equal, x has to equal 9. Well, that's a simple case, but let's look at one that's a little bit more complex in terms of what we put into those exponents. So instead of just x in the exponents, now we have full expressions of x in the exponents. But that doesn't mean that our process changes. We still need to find a common base, just like we did with 4 and 64. Well, 5 and 125 are related to each other as well. In fact, 125 is 5 cubed. So now on the right-hand side we have 5 to the 3rd power, all raised to the x plus 2 power. We should do exactly the same thing we did in the previous problem, multiplying the exponents. We have to be careful here, though, because 3 times x plus 2 involves distribution. It can be very easy to end up here with 3x plus 2 instead, but we need to multiply the complete exponential expressions. Let's see what this leaves us with. So now we have 5 raised to the 5x power on one side, and 5 raised to the 3x plus 6 power on the other side. But we have common bases. So we can make the step given by the property above, and simply set those expressions in the exponents equal to each other. Now it's just an algebra problem, thank goodness. We can subtract that 3x from both sides, and divide by 2, and we've solved it. Slightly more complex, but the game with all of these problems is simply finding that common base. Let's take a look at a few problems that are very similar to the ones that we did in the previous videos, but this time let's formalize our language just a little bit. We've looked at several problems where we know that a certain quantity grows by a certain percent or declines by a certain percent every time period. And we'll recall that this fits the pattern that we had before. But remember, if we had an increase, for example, of 10% per time period, that implied... But remember, when we were talking about growth at a rate of 10%, we turned that b value into 1.10, not just 0.10 as it would be if our common ratio were 10%. What this is saying is that every time period, the value that we have becomes 110% of what it used to be. That's what 10% growth means. So we can write this out actually in a general form and say, for percent growth, that this is how we set up that exponential expression. A is still our initial value, but here P is now the percent growth rate. This makes it very easy for us to solve problems in which things are growing at a certain percent every year. Think of interest on a bank account. Think of the value of some commodity. Whatever that percent increase is, we add 1 to it. And remember that our independent variable here is time, some number of units of time. We might be talking about weeks, we might be talking about every 23 days, we might be talking about every 6 milliseconds. But we're interested in changing that time period and seeing what kind of growth takes place. The reason why I want to formalize this now is that it actually helps us solve these equations for any of the variables that are contained in them. We might not know what A is, we might not know what P is, and we might not know how many time periods we are into this process. So any of the 3 variables could be unknown to us. But all we need to do is use this functional form, fill in the things that we know, and solve for what we don't. For example, let's look at growth in a population. At t equals 0, or when we start this observation of this particular population, f of t, which is just the population itself, is 1,321,045. Let's say this is the population of a city. When we started observing, we saw that this was the population of the city. 7 years later, at t equals 7, and let's say that t is in years, that population has grown to 1,512,986. the question we can ask ourselves here involves solving for p in the equation above. So let's write down what we know. When t equals 7, this is our population. So let's write that down as f of t. Well, all we need now is a, our initial value. Lucky for us, we're given that there at time equals 0. But the one thing we don't know here is that growth rate. So we have to leave that as a variable. But lucky for us, we do know how many time periods we are into this process. 7 years. Now we've come up with an expression where we only have one variable, and we should be able to solve for p. Well, if we want to get p by itself, I say the first thing we do is divide both sides by this quantity. Those are some big numbers. I think we should look at the calculator. That's what we had on the left side of the expression, and we wanted to divide that by 1.1453. Let's write that down. All right, we're getting there. The next step would have to be taking the 7th root of both sides, because we'd like to get that exponent off of the p if we're going to solve for it. Well, that really requires us to take the 7th root of this 1.1453. Let's go back to the calculator and do it with the number that we got there. So here's the number that we had, the 1.1453 number. Let's take the 7th root of that. In fact, let's do that in a slightly simpler way. If we're taking the 7th root, we're raising it to the 1/7 power. So let's just take the answer that we have and raise it to a rational power. 1.0196. All right, all we need to do to get p by itself is subtract 1 from both sides. And we've solved the problem. This p is our annual percent growth rate, since we had set the year as our unit. In the previous videos, we were mostly concerned with figuring out what the population was after a certain amount of time. But what this example shows is that we can actually solve for any of the variables in this equation, simply by inputting what we know and doing the algebra to solve for what we don't. I want to take a look at this example of compound interest because it's something that you're going to see in the growth of your own money in bank accounts, as well as understanding things like car and home loans. In the example we just did, the population increased by a certain percent every time period. It was a year in that particular case. But we can actually set up an expression that does very much the same thing, but allows us to say that that growth is going to compound several times during a particular period. So if you put a certain amount of money in the bank, and it pays 5% interest, but that interest actually compounds 4 times a year, you're making more money at the end of the year than you would be if you just got that 5% interest added on at the end of the year. Remember, this goes right back to what we talked about with the definition of exponential functions. The rate at which the function grows is dependent on how much stuff you have to begin with. So if we compound interest, that means that after the first quarter of the year, we're going to have more money to then build interest on. And after the first half of the year, we'll have more money again. But here's the definition for compound interest. It's a whole new set of letters, but I think we can understand it. A is the amount of money that we have after t years. So just like in the previous equation, we were dealing with t in years. But here, our initial value is called principal. Principal is just the amount that you originally invested. And in this case, r is the interest rate, expressed as a decimal, and n is the number of times it compounds. It might compound twice a year, every 6 months. It might compound every quarter, 4 times a year. It might compound every month. Heck, it could compound every second. But let's see how this works. Let's say that we invest $4,000. And let's say the return on that money, the annual interest rate, is 5.4%. Finally, let's say that that compounds quarterly, which means it compounds every 3 months or 4 times a year. Let's see how much money we're going to have after 8 years. And we can just use the equation as it appears. Make sure that you put that rate in there as a decimal. That's the number of times a year that it compounds. And we're 8 years into this process. Now this really just becomes a calculator problem. So we had our principal. And in here is actually our common ratio. I know it looks complex and it has a sum and a quotient in it, But our 4,000 is our initial value. And here, since this is still an exponential expression, is our common ratio. But we're going to raise that to the 4 times 8th power, the 32nd power. So in 8 years, our money has grown from 4,000 to $6,143.56. So we'll see some more examples about this. But it's good to keep this formula in mind, and to remember also that it has the same form that we've seen for all exponential functions. But in this case, b is a little bit complex, and the power that we're raising it to is in product form. You'll get a chance to work with a lot of problems like these, but I hope that these serve as a good example. Thank you, everybody.